so this is the outline for chapter 31. So we will introduce the LC oscillations, so which is a second order system, and also we will talk about the damped oscillations in an RLC circuit. So actually here we will actually compare this second order circuit with the second order mechanical system, like the spring mass system. The spring mass system, I think you should have learned it in mechanics. So we will have a brief comparison between them, and then we'll talk about the forced oscillation of the three simple circuits, including the resistor, capacitor, and inductor. So this part already related to the phasor, and actually it will relate to the Fourier series. I think you might need to learn it in something like engineering math course later on. Yeah, but actually it's related to the Fourier transform or Fourier series. So actually for the Fourier series, it will be quite useful for engineering students, because we try to analyze the signal in frequency domain rather than time domain. Yeah. Okay. And for linear system, it will be especially useful. And then we'll talk about the RLC in series. Actually, here is also RLC in series, but we'll talk about when we have input to be sinusoidal, then we can quickly know what is the response for the RLC circuit. Here we talk about the RLC circuit without source. We just try to store some energy there, and then we try to have a natural response, something like that. So then we'll talk about the power in AC circuits, and then the transformers. Okay, so here we have quite a complicated figures on the right side. So let's take a look at one by one. So let's start here, because this is figure A. Okay, so we start at here. So let's see. It says 8 stages in a single cycle of oscillation of a resistanceless LC circuit. LC circuit means it only has a L and C in series. We don't have a resistance here, because this one is more simple. It's simpler because it don't have any loss. Resistanceless means lossless. We don't have any power loss in this system. So with this assumption, then actually for this circuit, it will oscillate forever. Something like if you have a spring, and then if the spring doesn't have any loss, then the spring, if you just try to drag it a bit, and then it will just oscillate forever. But if there are any loss, then it will gradually stop. So it seems something similar in this case. Okay, so here the magnetic field lines of the inductor and the electric field line of the capacitor are shown. Okay, so for part A, we can see here also mentioned about the energy stored in the capacitor, or stored in the E field, and the energy stored in the magnetic field or in the inductor. Okay, so here initially we don't have any current, and then all the charge are on the capacitor. So you can imagine there will be a potential difference across the capacitor. So the UE, do you remember what is UE? UE will be half of CV squared. And then, can you remember UB? UB will be half of Li squared. Li squared. So initially we don't have any current, so there is no energy stored in the B field. So you can see this is 0, and then this is full, half of CV squared. So this is the initial moment, and then the charge will go in this way. The charge will discharge. The capacitor will discharge. So there will be some current, because if you still remember, I is dq dt. So if the charge amount is changing, then there will be some current. So as it will start to discharge, then there will be some current. So I is counterclockwise for figure B. Okay, maybe let me just enlarge it a bit. Okay, so it will start to discharge, and then there will be some current. So in this case, the charge amount become less. So the E field here also become smaller. And then, as much as there are some current going through the inductor, there will be some magnetic field generated by this inductor. So here, you can imagine half of Li squared. So it becomes a positive value, and then half of CV squared becomes smaller, because V becomes smaller because there is less charge. So if you still remember, Q equals CV. So if Q becomes smaller, V also becomes smaller. So here. Okay, so for a single moment, so actually the UE is decreasing and the UB is increasing. So for a single moment, then UE and UB will equal to each other, but just for a single moment. Okay, so actually during this procedure, UE decrease and UB increase, but just for a single moment they are equal to each other. And then for the next stage is the charge. The charge is further decreased up to zero. So in this case, the current become maximized. So in this case, there is no voltage difference across the capacitor. So UE becomes 0, and then I is maximized. So all the energy transfer to the B field. So it's just like all the energy stored in the E field is transferred to the energy stored in the B field. So this is the situation here, and then it will further discharge in the opposite direction. So if you like, it's try to charge some positive charge on the bottom plate rather than the top plate. But actually the current will be smaller than this situation. But actually you can imagine, this is V. So V is a negative value. But when we consider the power or energy stored in the capacitor, it is half of CV squared. So even though V is negative, then taking the square will be a positive value. So here the UB will decrease and UE will increase. And then for this procedure, so for a single moment also, we will get UE equals to UB just for a single moment. And then it will further charging the capacitor, and then so all the charge is go to here. So UE become maximized again, and UB becomes 0. So for this moment, I equals 0. And then we can just going forward, just the other way around, and then UE becomes smaller, becomes 0, and then becomes larger again. So, and then going back to this situation, and then for UE you can imagine, UB you can imagine UB larger, and then maximize, smaller, 0, and then become a positive value, and then maximize again, and then going back. So just like a oscillation, the energy between the stored in the E field and B field are transferred to each other alternatively. Okay, so yeah, so just as I mentioned, UE is actually Q squared over 2C, or half of CV squared. So I think there is nothing special, and it just mentioned that it is said to be electromagnetic oscillation. Okay, so here we will talk about, we will try to compare this LC oscillator, or the electromagnetic oscillation, with the block spring system, or usually I will call it a spring mass system. Spring mass system rather than block spring system. Okay, so here, the LC oscillator, we have some energy stored in the capacitor. So this energy is half of CV squared, and then for the inductor, the energy stored in the magnetic field is half of Li squared, and then we have I equals dq dt. And for the spring mass system is something like this. Or maybe try to put it horizontally. So suppose we have a spring, and then we have a mass. So this is m, and then the coefficient of the spring is k. So if you still remember the Hooke's law, is F equals negative kx. Okay, so the energy stored in the spring will be half of kx squared, and then the kinetic energy of the mass will be half of mv squared. So here you can see x and v, the relationship between them is the first derivative. So we take the first derivative of the displacement will be the velocity, and then here also you have q, we have I here. When we take the first derivative, it becomes I. Or actually we can, if we just use v and I, then we still have I equals c dvc dt, or L equals or v vc dt, or VL equals L di dt. Yeah, something like this. So it's still a first derivative between the variable. Okay, so here it says, from the table we can deduce that the corresponding between those systems, thus Q correspond to X. So which means that if you just change X to Q, and then 1 over C to K, or K to 1 over C, and then M to L, then yeah, what we get in that system can apply to here. So we may not need to derive it again, but yeah, and actually for the oscillation frequency of the LC circuit, it is nothing but omega equals 1 over square root of LC. And yeah. But here I just So here in the textbook, it also mentioned about the energy method. I think it is quite interesting, although actually I have thought, I don't remember I have learned this energy method before. Yeah, but I think it makes some sense, and of course it is correct, and it's quite interesting. So I just let you know a bit. So it says the total energy in the system is defined as U, and then for the oscillator, LC oscillator, it of course included UB and UE, the energy stored in the B field and the energy stored in the E field. So the UB is a half of Li square, and then the UE is Q square over 2C as mentioned, or half of CV square. But in the textbook, it just use Q square. Okay, so it says, yeah, so this is the definition, and then it says, since we have assumed the circuit resistance is zero, to be zero, so no energy is transferred to thermal energy. So which means that if we take the derivative of U with respect to time, it should be zero because U doesn't change with the time. So it is so-called the conservation of energy. So we can just have a du dt equals zero. So actually U has this expression. So we try to take the derivative of these two terms with respect to time. So here we have L. L is a constant, and then I is a function of time. So we need to take the derivative. So I squared, when we take the derivative, is 2I. So 2I, the 2 can be cancelled with this half. So we have L times I. And then we need to consider the chain rule because it is just a function of time. So we need to multiply it by di dt due to the chain rule. And then for the second term, C is a constant. So C just put here. And then Q squared. Q is a function of time. So when we take the derivative, it becomes 2Q, and then 2 cancel with this 2 also. So we have Q over C, and then also we need to consider the chain rule, so we need to multiply it by dq dt. So the expression look like this. And then we also consider I equals dq dt, and then we can just plug it here. So the first term becomes so here, when we try to plug in I equals dq dt, it becomes L dq dt, and then take the derivative of this one. So di dt will be the second derivative of Q. So we have the second derivative of Q with respect to time plus Q over C dq dt equals 0. Okay, so here we just cancel dq dt because we assume that dq dt is not 0. It's not 0. If it is 0, then there is nothing. So we just cancel that term. So finally, actually we also divide L on both sides, so that we have a second derivative of Q plus 1 over LC times Q. We just put the Q here. So it is actually a second order ODE, and it is actually a homogeneous equation because we only have 0 on the right side. We don't have any excitation. We don't have any sources or battery. So so it is just a homogeneous second order ODE. Okay, so actually we can use the potential method, or actually use the KVL to get this expression. Okay, so in that case, we try to draw the equation, draw the circuit diagram like this. So actually we only have L and C, and then we assume this to be the V. The V is the voltage or the potential across the capacitor, and then we make this I to be the current going clockwise. So actually this is V. This is negative V. This should be negative V. So this is V. From here to here should be negative V, and then because from here you go up by V and then go down by V back to the original point, so this should be negative V. Okay, so here first we can have I equals C dV dt. When we consider the capacitor, the current is going this way, and then V is in this direction, so I equals C dV dt. And then for the inductor, I is in this direction, but V is here is negative V. So here we have a negative V equals L di dt. Yeah, we have this minus sign because this is negative, or maybe I can just highlight it in red color. We have a negative sign here, we have a negative sign here. Okay, so actually we can just plug in this equation into this one, or the other way around, which will be actually the same. So okay, so let's try to plug in the left one to the right one. Okay, so in this case we have a negative V equals L di dt, so d dt, and then we have the C dV dt here. Okay, so C is just a constant, so we can just put it out. So we have LC, and then the second derivative of V with respect to time. Okay, so we can just slightly rearrange the term, and then we can actually divide 1 over LC, divide LC on both sides. Okay, so we will get d2V dt2 plus 1 over LC times V equals 0. Okay, so actually this is a little bit different. It's a little bit different from this one. This one we have Q here, but here we have V here. Actually, you can also try, if you try to plug this one back to here, maybe I just use another color. If you try to plug this one back to here, you will get something like I equals C dV dt. So V is a negative L di dt. Okay, so L is a constant, so we have a negative LC, and then d2I dt2. And then we also divide LC on both sides, divide LC, not divide 1 over LC, divide LC, divide LC on both sides. So you get d2I dt2 plus 1 over LC I equals 0. So actually this is so-called a linear circuit. So for any variable here, for example, the voltage across this one, the current or whatever, then it will also satisfy this equation, including the charge. Because you can also imagine I is dq dt, then you can just plug in here, and then you will find it to be d3q dt third, and then plus 1 over L dq dt. So you can just integrate on both sides to get rid of one of the derivative, and then you will also get this one. So this is how we try to derive this simple equation. And then actually for the spring mass system, we can also do similar things. Like suppose we have this spring K, and then this is M. This is M. Okay. So yeah. So if you try to drag it up to x, so we will have f equals negative kx, f equals negative kx, and then f is actually ma, f is actually ma. So we will get f equals negative kx equals ma. So due to the Newton's second law of motion. Okay, so actually the acceleration is the second derivative of the displacement. So we have a m d2x dt2. Okay, so we can try to divide m on both sides. We'll get d2x dt2 plus k over m x equals 0. Actually, we can try to solve for this equation, and then this is a homogeneous equation, so we don't have a particular solution. So actually, for the second derivative, we change it to s squared, and then k over m, and then x, we change it to 1. Okay, so we will get s equals to j or I, which is just the square root of 1, and then square root of k over m, because both k and m are positive value. Okay, so here we know that x should be a cosine of, or maybe we can just call omega to be square root of k over m. So we can write it as a omega t plus b sine of omega t. Actually, in high school trigonometry, you know, suppose you have cosine and sine with the same frequency, you can actually write it as r cosine of omega t plus phi, something like that. Because this one is nothing but a cosine omega t cosine phi minus sine omega t sine phi. So as much as you need to make this one, so you try to divide and multiply this one by r equals square root of a squared plus b squared, and then you can just make this coefficient and this coefficient to be sine phi and cosine phi, so that you can make it like this. Okay, so this will be the similar the familiar equation for the simple harmonic motion. So which is just a sinusoidal function. And of course, so you can just compare this equation with this one. They look actually the same. The only difference is that here we have 1 over LC, here we have a k over m here. So for that case, omega is 1 over square root of LC rather than square root of k over m. Okay, let's have a 10 minutes break.